In this video, we are going to explore complex numbers, and that means today that we are going to be simplifying square roots that use imaginary numbers. We are going to simplify complex expressions by performing operations with the imaginary numbers, and we're going to use conjugates again today, but this time they're going to be complex conjugates, meaning they have imaginary numbers in them. Okay, so first we need to talk about what the word complex number means. So the idea is that not all quadratic equations have real number solutions. Remember when we were graphing and you had a parabola that looked something like this. There was nowhere that it crossed the x-axis. And so we would say for these that there are no real solutions. And the reason that we put the word real in there is that because when we extend our understanding of numbers past real into complex or imaginary numbers as well, then we can get solutions, even though it's not really crossing the x-axis anywhere on the graph. All right, so let's talk about what this means. Mathematicians decided to make up a number, an imaginary number, and they're going to use the letter I to stand for this number. So anywhere that you see the number I, that is equivalent to the square root of -1. This is the definition of the imaginary number I. You can rewrite I as the square root of -1 anywhere you see it, or vice versa. That means then that if you have I squared, that's the same thing as squaring this square root of -1. And if you square a square root, that leaves you just with the radicand. So that means I squared is equal to just the radicand -1. Now what we're going to be working with today is going to use this idea, this definition, a lot. We're also going to look at complex numbers, which means it has a little bit of a real number in it and a little bit of an imaginary number in it too. So you will see numbers in these places where there's a and b, but one of the pieces is going to be multiplied by that imaginary number or the square root of -1. So let's look at some problems now. If you would like to use the imaginary unit I, you are going to use it anytime that we have a square root of a negative number. You probably remember from previous math classes like Algebra 1, anytime you had a square root of a negative number, your teacher said you can't take the square root of a negative number. And that's true in the real number system. But because we're working in the complex number system, that means that this negative number 1, this -1 times r, can come outside as an I. So let's look at what that means. If I have the square root of -6, that's the same thing as the square root of -1 times 6, right? Because -1 times 6 is -6. According to the definition, the square root of -1 is I. So this simplifies to I square roots of 6. Now in this next one, you have a power. You have two things that are being multiplied together. I times the square root of 3, all raised to the second power. So that's the same thing as I squared times the square root of 3 squared. Recall from a moment ago that I squared is equal to -1. So I'm going to rewrite that as -1, and then any square root that's squared leaves you just with the radicand, which is 3. So that means I have for my final answer -1 times 3, which is -3. Let's try one more of these. The square root of -81. That's the same thing as 81 times -1, right? The square root of 81 then is 9. And the square root of -1 is I. So that's 9 times I. When we do operations with complex numbers, you have to be kind of mindful of this imaginary unit I. So let's talk about what I means. It has this nice rotational element that happens to it. I to the first power is just I. We've talked about I squared. I squared is the square root of negative 1 times the square root of negative 1, which is just going to leave us with negative 1. If I take negative 1 and I multiply it by I again, that's going to give me negative 1 times the square root of negative 1, or negative I. And if I raise negative I again, or multiply it by I, that's going to give me 1. And this cycle is going to continue to be multiplied through, or followed through, as high as I get. I can keep raising to a really high power, and it's going to give me one of these 4 answers that it cycles through. So let's look at this, because you're going to likely have to solve one of these on quizzes and tests and the SOLs. If I have I to the 100 power, I don't want to cycle through this all the way up to 100, so let's use the exponent rules from before. I to the 100 is the same thing as I to the 4th times I to the 25th, right? Because 4 times 25 is 100. I to the 4th is 1. And I to the 25th, well, rather than doing it that way, that means I can write it as I to the 4th power times 25, or times the 25th power. So I can raise that 4 to the 25th power. This is 4 raised to the 25th because it's 4 times 25. Okay, so like that. Now let's change that. I to the 4th becomes a 1 based on this up here. And 1 to the 25th power is equal to just 1. If I do I to the 501st power, that is the same as I to the 500 plus 1 using the exponent rules. And according to the exponent rules, if I'm adding together 2 powers, that's the same as multiplying the 2 same bases. So that's I to the 500 times I to the 1st power. I to the 500 is I to the 4th raised to the 125th, that's power times power, times I to the 1st power. I to the 4th again is 1. 1 raised to the 125 times I gives me just 1 times I, which is just I. Okay, now I bet your head is spinning a little bit here, right? So this first row is something that if I were you, I would memorize. Because if you have to solve these by hand, then you can use the exponent rules from a previous class to create a power that is much easier to deal with. Now here's the other great news. If you grab your calculator will do some of this work for you if you are in the right mode. So on your calculator, I want you to hit the mode button, and you'll see that there is this option down here where it says real and A plus BI. You need to change your calculator from this point forward in Algebra 2 to the complex number system, or A plus BI, the imaginary mode, every time you use your calculator, so that it allows us to work with these imaginary numbers. Your calculator is going to be set in real initially. Change it every single time. When you make that change, you'll see when you close out, so I'm going to go to second quit, up at the top here, it says A plus BI instead of real. That's really good. That means I'm in A plus BI, or complex mode. So now let's try this I to the 100 problem again. You'll notice on your calculator down here in blue above the decimal, there's this blue I. That's the imaginary number button. So I'm going to hit second decimal to put the I on my calculator, and then I'm going to use the caret to raise it to the 100th power. When I hit enter, it's going to tell me that's going to give me a 1. If I do I raised to the 501st power and hit enter, it's going to give me, look at that, a kind of weird, ugly scientific notation number. If I have 4.9 e to the negative 12, that's a really small scientific number. That decimal place gets moved 12 units to the left. So that's a 0.00000, a whole bunch of O's, 49. That's really close to 0. It's a really small fraction. And that really small, close to number 0 is being added to I. So if we round, if we say this is like 0, 0 plus I is just I, and that gives you your answer here. So know that these problems where you're raising I to a really big number, if you have access to a calculator and your calculator mode is set to complex number systems, the calculator will solve these for you. Okay, so let's go back to our notes now. Okay. All right, so let's add and subtract parts that have complex numbers. So one thing that I do want to emphasize is that when you're doing operations, you should first treat the imaginary number I like a variable, and then do any simplifying you can with it after you've done the other work here. So when I do these operations, notice I have this complex number, 4 minus I, that's being added to this other complex number, 3 plus 2i. So because it's addition, these parentheses that are holding things together, they don't tell me anything especially important. This is the same as 4 minus I plus 3 plus 2i because of the properties of parentheses and addition. So that means I can combine like terms. I can do 4 plus 3, which is 7, and negative I plus 2i. If I think about that as negative x plus 2x, since I'm treating it like a variable, that's the same thing as just x. 2x minus x is x, so that means negative I plus 2i is just going to be positive I. So my complex number simplifies to 7 plus I. In number 2, notice that this one is this first complex number minus the second complex number. So we need to deal with this minus sign first. We need to distribute that negative 1 in. So that's going to be 7 minus 5i minus 1 plus 8i. The same way that we do in all of the other simplification of like terms, distributive property, everything that you've done in the past. Now again, we're going to look for like terms so that we can add and subtract them. I've got 7 minus 1, which is 6, negative 5i plus 8i, so that's positive 3i. Again, that I is acting just like a variable in this context. Let's try some multiplication now, where the i's are going to behave a little bit differently. If I need to multiply 8i times 3i, I can use the distributive property. So I can distribute these and multiply the stuff that's common together. So I can do 8 times 3, which is 24. I times I is I squared. Now, you have to remember that definition. I squared is negative 1. We need to substitute here. 24 times I squared is the same thing as 24 times negative 1, which means my answer is negative 24. Look at number 4 now. This one has 5i times a complex number, negative 2 plus I. So we're going to take that 5i and we're going to distribute it to both things in parentheses now. 5i times negative 2 is negative 10i, and 5i times positive I is positive 5i squared. Don't forget to multiply the I times the I. I have some substitution I need to do by using that definition. This I is stuck. There's nothing else I can do with it, so I'm going to leave that negative 10i. But this 5i squared is going to change to 5 times negative 1, which is negative 10i minus 5. Now, I'm also going to point out here, traditionally we write it with the I at the end. So I'm going to change this by just swapping the position around to negative 5 minus 10i. Not mandatory, but just like we don't write 5 is equal to x most of the time, we write x is equal to 5. That's the traditional way of writing it, and here's the traditional way of writing this. Okay, let's move on from multiplication into our last piece, division. Now with division, we're going to have those conjugates again. This time they're going to be complex, meaning that you're going to have two terms potentially being added or subtracted. One of them is going to have an I in them. We're going to approach these the same way we approached the radicals in the previous notes that you watched. So we are going to use a conjugate with the opposite sign holding together the two terms. So in this first one, I have 3 minus 2i divided by 5 plus I. I need to get the I out of the denominator because that is not in simplified form if there's still an I there. So I'm going to multiply by the conjugate, 5 minus I. I'm going to do that on both the top and the bottom. And I'm going to have to do a bunch of foiling now. I'm going to FOIL the top two together. I'm going to FOIL the bottom two together. Because I'm multiplying by the conjugate, I'm going to have some nice canceling out that happens in my denominator. So let's start with our numerator. FOILing these together, 3 times 5 is 15. When I do my outside, 3 times negative I is negative 3I. Remember, right now I'm just treating the i's like variables. Negative 2I times 5 is negative 10I. And my last terms, negative 2I times negative I is positive 2I squared. Don't forget, I times I is I squared. When I do my denominator now foiling, 5 times 5 is 25. 5 times negative I is negative 5I. Positive I times 5 is positive 5I. And my last I times negative I is negative I squared. Don't forget that square. Okay, so now we're looking for like terms. In the denominator, do you see this negative 5I plus 5I? Those are going to cancel out. In the top, do you see any like terms? I see these two here, negative 3I minus 10I. So if I'm treating that I like a variable, that leaves me with 15 minus 13I plus 2I squared. In my denominator, I have 25 minus I squared. So I've done all I can here, but now I need to do the substitution. Remember, what does I squared equal? It equals negative 1. So I'm going to substitute in now for those I squareds. 15 minus 13I plus 2 times negative 1 divided by 25 minus negative 1. So simplifying further, I've got 15 minus 13I minus 2. So I'm going to have some like terms up top that I need to combine. And in the bottom, I've got 25 minus negative 1, so that's plus 1. So when I combine my like terms, 15 minus 2 is 13 minus 13I over 26. And now I'm not quite done because I have a GCF. In my numerator, I can take out a GCF of 13. That leaves me with 1 minus I. 13 is divisible by 26. 13 plus 13 is 26. So those divide out, and in the bottom, I'm left with my numerator of 2. Which means my final answer is 1 minus I divided by 2. All right, so I know that was a lot. Let's recap that. You multiply by the conjugate to get the I out of the denominator. When you multiply by the conjugate in the denominator, you do it in the numerator too. That's going to make the i's in the denominator subtract out. Don't forget that once you do your combining of like terms, you have to substitute in negative 1 wherever you have an I squared. Once I do that, I simplify, I combine like terms again, and I look to make sure my fraction won't reduce at all. Okay, so why don't you give the Now You Try problems a try? You have the ability to simplify square roots using imaginary numbers. Remember, you can take the square root of a negative number, like negative 81, because the negative square root, or the square root of negative 1, is I. And you can simplify that. You can simplify complex expressions by performing operations involving imaginary numbers. Remember, the imaginary number acts like a variable first, and then you can simplify it further. And finally, you can use complex conjugates to simplify rational expressions if there's an imaginary number in the denominator. So go ahead and give those a try now.